My name is Yoshiharu Morimoto. My nickname is Harry Moiré. I'm a professor emeritus at Wakayama University. And also I am a chairman of 4D Sensor Inc., Wakayama, Japan. The co-author is Mona Yadi from Iran, Masaki Ueki from Japan. They are our colleagues in 4D sensor. We'll show the car vibration distribution and tuning fork vibrating amplitude distribution. This is the outline of my presentation. I'll talk purpose and background. Then I'll introduce grating method and moiré method and phase analysis. Especially, I'll introduce one pitch phase analysis method, OPPA method, or out-of-plane deformation measurement. So we applied this method to cantilever plate and car with out-of-plane vibration. And also, I will introduce sampling moiré method for in-plane deformation measurement. We apply this one to the vibration measurement of tuning fork, which has a in-plane vibration. Then I'll conclude and give future work. So I'll present a purpose and background. My company name is 4D Sensor. 4D is 4 dimension of XYZT. That is, we can measure 3D shape XYZ. So we can measure very quick measurement. We have a very quick measurement method. So 4D means time-dependent 3D shape measurement. So we developed many high-speed shape and deformation measurement systems. So in factory, sampling inspection is very popular now. But by using our method, we provide online full inspection method. By using this method, we can provide short-time measurement of moving objects, measurement from moving objects, experimental vibration modal analysis, visualization of invisible defects, experimental wave propagation analysis. So this photo shows the object in the production line. This object is moving on the production line, conveyor belt. We can measure the shape in real time for the moving object. And we also can measure the moving human body shape. And we can also measure the vibration of machine. In this study, we developed modal analysis system for vibrating objects. Next, we'll introduce grating method and the moiré method. This is a typical grating projection system. We call moiré topograph. Here is the light source. Here is the grating. This grating shadow is projected on the reference plate or projected on the object. The shadow of the grating image is recorded by this camera. So this is the grating image projected on the reference plane. This is the grating image it's deformed according to the shape. By analyzing this deformation, we can obtain the height distribution. By superposing this grating, deformed grating and straight grating, we can obtain moiré fringes. By analyzing these moiré fringes, we can obtain the shape distribution. And also we can analyze the shape by using this deformed grating image. The phase analysis of the grating image, we can obtain this phase distribution, and also we can obtain the phase information of the moiré fringe. So from this phase distribution, we can obtain the 3D shape very accurate. So this grating analysis method is grating method. This moiré fringe pattern analysis is moiré method. Next, we will introduce phase analysis. This is a grating projected on the object. The grating is deformed according to the height. So this fringe pattern is a magnification of this area. So the intensity distribution is given by this graph. So white parts and black parts, white parts and black parts. So the first white position, the phase is 0. Next white peak is phase is 2 pi, 4 pi, and 6 pi. So by analyzing the phase distribution of this graph, we can calculate a very accurate shape. So the intensity is given by this equation. A is the amplitude, theta is the phase, B is the background intensity. A, theta, B is unknown. So if we change the condition more than 3 times, we can detect the this unknown A, theta, B. So usually we use the phase shifting method. This fringe pattern is shifted plus alpha. So usually we use the 19 degrees. Then we can obtain each 19 degrees by 4 times shifting. We can obtain 4 intensities. From the 4 intensities, we can decide the A, theta, and B. So theta gives the shape information. So phase analysis provides accurate shape. The resolution is 100 to 1000. In good, very good condition, we can obtain 1/10,000 of each. So the accuracy becomes very high by analyzing the phase. In this study, we introduced one pitch phase analysis method, OPPA method. Phase is analyzed from one pitch data of the projected grating in a single shot image. The one pitch is easily extracted using a moiré topography optical system. In order to analyze the phase, the brightness data of continuous pixels are used. Calculation speed is very high. It is possible to analyze the phase in real time. So we can measure the shape in real time by using OPPA method. It provides high speed and accurate measurement. Next, I will introduce the theory of one pitch phase analysis method for out-of-plane deformation measurement. This here shows the phase shifted to grating image. In this case, phase is shifted 9 times for one cycle, for one pitch. At any point, for example, this endpoint, the brightness changes by phase shifting. There is a white and black and next to white. So the brightness changes like this, sinusoidal. By analyzing this initial phase, we can analyze the shape from the initial phase. So by using this 9 brightness data, we can calculate the Fourier transform. The Fourier transform gives a Fourier spectrum. And if we extract frequency 1 and frequency 2, 3, and 4 is eliminated as a noise, then we extract only frequency 1 and calculate the phase information, and it gives a very natural, very smooth sinusoidal wave. From the phase value, it gives very accurate shape information. But in this case, during the phase shifting, object should not move. It must stop. So if the object is moving, such case, we cannot use this phase shifting method. So our OPPA method can analyze only one image brightness data. For example, if we use this blue point continuous brightness on a line, the brightness changes like this for sinusoidal. From this 9-point data, we can analyze the phase, initial phase, this one. So the last, next phase is this value. From this value, we extract only one cycle data, which gives us this red phase is equal to this blue phase, because this one is one pitch. So the initial phase is next 9 pixels initial phase is the same. So this red phase and this blue phase is the same. So we can analyze this phase value from this data. Then we can analyze the phase value from one single shot image. So this analysis method can apply to moving objects. If we can take one grating single image, we can analyze the phase distribution. So we can obtain the height distribution from single image. But the phase shifting method analyzes the initial phase. But our OPPA method analyzes this phase at the center of the position. So the center of the position gives the phase is given by this equation instead of Fourier transform. So this equation gives the extraction of frequency 1 to obtain the phase value. This is the same value is obtained. This is a typical optical system for OPPA method. Here is a projector. Light source is here and grating is here. This grating shadow is projected on the reference plane or on the object surface. This is a schematic explanation here, magnified of this one pitch. here is a grating one pitch AB, and this shadow is projected on the reference plane as CD. Here is a phase 0. This is a phase 0 line. And next bright line, here is a phase 2 pi. So the phase 0 to phase D, 2 pi. So this is the one pitch. The one pitch length is different according to the distance. CD is longer than EF one pitch on the object. However, if we take this one pitch by this camera, in the image plane, the CD length is recorded as a length GH in the image plane. EF is recorded as IJ in the image plane. Such case, the length GH is IJ is the same according to this geometric relationship. It's easy to calculate the relationship by using this triangle simula. So the calculation is not so difficult. Then we can obtain the one pitch is every time it gives 9 pixels for one pitch. It doesn't function of the height. If any height of the object, if we extract one pitch, that's a constant pixel number. So at first we adjust the one pitch for 9 pixels, for example. In our case, we use 9 pixel is most popular number. So at first we adjust one pitch 9 pixels. Object movings or object height is different, but if we extract 9 pixels, it gives only one pixel, just one pixel pitch, one pitch. From one pitch data, we can calculate Fourier transform. The one pitch data is not this 9 pixel or integer. The Fourier transform has an error, but this one is integer. Such case, the Fourier transform gives very accurate phase information. And this is a camera 1 pixel point view line. So in this case, the phase, here is a phase 0. And here is a phase almost about 150 degrees. And here is a 360 degrees. So the height is according to the phase. Phase is according to the height. So if we calculate the phase, the height is obtained this equation. This equation is obtained the relationship between these triangles. So the parameter pitch and theta is a phase difference between this phase and this phase. And dr is the height of the distance of the light source and reference plane. V is the distance between light source and camera center, camera lens center. So from these parameters, we can calculate the height from the phase theta. In the optical system for multiplicity, if a grating pitch is adjusted so as to be n pixels, the pitch of the grating image is n pixels at any height. Only the phase of the grating image is different according to the height. Therefore, The Fourier transform of the brightness data for one pitch of the grating provides the accurate phase, that is, the accurate height. So this is a schematic image of the grating pattern. So if we extract one pitch data, for example, in this case, 9 pixels, from these 9 brightness data, by calculating the Fourier transform, we can obtain Fourier spectrum, frequency 0, frequency 1, 2, 3, 4, and -1, -2, -3, -4. By extracting frequency 1 and erase other frequencies, then calculate the phase. The phase is stored in the other memories in the center of the 9 pixels. Then we move this 9 pixels on the whole surface. Then we can obtain the phase distribution on the whole surface. From the phase value, we can calculate the height by using the last equation. So it's easy and very fast to analyze the phase value. So Fourier transform of the small pixel number, the calculation speed is very high. But the Fourier transform, the pixel number is too much. Such case, the calculation of the Fourier transform is not so high speed. But in this case, 9 pixels is very small, so the calculation speed is very high. This is an example of the accuracy check of one pitch phase analysis. So the dynamic range is 9 millimeter in this case. So we measure the every 1 millimeter height. So the error is at 9 millimeter. The error is 136 micrometers, and standard deviation is 28. The standard deviation is almost 1/300 of dynamic range. H is 9 millimeters. So the accuracy is not so bad. By using this OPPA method, we developed real-time motion capture. And also we developed vibration distribution meter. We use the high-speed camera, so we can measure the shape, 2,000 shapes in a second. But in this case, it's not real time. We analyze the grating image in batch process. Then we can analyze the human body and car parts. So this is an example of the moving human shape. Here is a grating image. Can you see the grating? So we project the grating by using ordinary projector. This is a projector. Here is a camera. So the camera records the projected grating image. Then the data is sent to personal computer. It gives a real-time 3D shape with pseudo color, like this. Next, we apply this method to cantilever plate and car without plane vibration. This is our first measurement system for vibration distribution data. Here is the light source. The light is come to this point through optical fiber. the optical fiber, each thread is aligned in linear. Then we can obtain the very thin linear light source. By using this light source, here is a grating. The grating shadow is projected on this specimen. So by recording this grating image by using this high-speed camera, we can obtain the vibrating grating image. In this case, the specimen is aluminum, and this end is fixed on this heavy basement, and this end is a free end. So we hit this one position, then this cantilever plate is vibrate. The vibrating fringe pattern is recorded by this high-speed camera. So this is the image of the obtained image, brightness distribution. This end is a fixed point. This end is a free point. So the fringe pattern move only a little. So we can see the vibrating fringe pattern, but the analysis gives a height distribution. And this graph shows the brightness distribution at one point, brightness change. And this graph shows the height change at this pixel point. So height is changing like this. So by analyzing this wave using Fourier transform, we can obtain Fourier spectrum like this. In this direction shows the frequency, and this direction shows the power. Power is the scale of amplitude. So at the resonance frequency, natural frequency, the local peak of the amplitude is given like this. This is the first local natural frequency. This is the second natural frequency. This is third natural frequency. And here is the fourth natural frequency. This one shows the phase distribution. At the natural frequency, the phase changes graphically like this. So from this one shows only the first mode image. So here is a fixed point. Only this point moves, and the phase is a constant for all surface. So it's move very natural movement. But the second mode, the frequency is 166. Such case, this blue is not move. Red is moving very large. In this case, phase is different according to this center line. So this one gives a rotating vibration. The third mode, it's almost 250 Hertz. Such case, here is a node. This position is not moved. And here is a moving points. So it gives a different pattern. And fourth mode, 543 Hertz, it gives a different pattern. But in this case, this mode is obtained by combined with this one and this one. So we can obtain the power distribution and phase distribution at 543 Hertz position. This is the first mode. By analyzing the vibration using finite element method, we can obtain almost same data like this. And the resonance frequency is almost the same, a little different, higher mode. So we check the resonance frequency by OPPA method and laser displacement meter, and theoretically finite element method, and theoretical numeric method. The whole natural frequency is almost the same. So our method is very accurate. This is a specification of our OPPA vibration modal analyzer. So the area size is 240 millimeter by 240 millimeter. The dynamic range is plus minus 5 millimeter, 10 millimeter. So if we use a high-speed camera, we can analyze 2000 Hertz frames per second. We can obtain that 2000. But if we use a low-cost camera, 300 to 700 Hertz, so the vibration speed is the half of the this value, and the accuracy is 10 micrometer. But if we analyze the Fourier transform, and each frequency gives a very accurate result, less than 1 micrometer. So the system is very high speed, and the theory is very simple, and the cost is very low. So usually, people use vibration analysis, this accelerator or laser displacement meter. But in order to obtain the distribution, this accelerometer is changed to the position several times, many times. Then it gives many big data, and it takes much time, and the calculation is very difficult and time consuming. And here is a distribution measurement system. It scans the point, but the speed is not so high. Only 400 points per second. It's very slow, and the cost is very high, very expensive system. And the scanning method cannot analyze transient phenomena. But our OPPA method can analyze same time. So there are 260,000 points, but all points have the same time data. So our system can measure the very high density. It's similar to the 260,000 accelerometer systems. So the distribution is very high intensity. We applied this method. Here is the projector, and here is the camera. We project the grating on the engine and front grille head cover. So we analyze this area's vibration. And also we projected the grating on the two doors, front door and backside door. We analyze the vibration This is the grating image. So the brightness of this PowerPoint is not so good, but we can obtain the fringe pattern here and here. Here is the front grill. Here is the edge. So at first the height is the same. Height difference is the same, almost zero. Next, we can obtain the height distribution as the engine is rotating. Then here is a very high power. The amplitude of the vibration is very large in this red area, and blue area, the vibration amplitude is very small. Here is a phase distribution. Phase is almost the same in this case. This is a door vibration measurement. This is the front door, and this is the back door. So the height change is at first it's uniform, but by vibrating the 2500 RPM, such case, the amplitude of the vibration in front door is very large, but back door, the amplitude is very small. The phase is almost the same, but in this case, if we change the phase distribution, it gives a phase moving. In this case, this position is moving like this. So we can easily detect the movement of the vibration. Next, I'll talk about the sampling moiré method for in-plane deformation measurement. This one shows the sampling moiré method theoretical treatment. Here is a grating on the object. So, if we measure the out-of-plane displacement, we project the grating. But if we want to measure the in-plane vibration or in-plane displacement, the projection cannot change by the in-plane deformation. So we use grating on the surface of the, we must place the grating, or we must draw the grating on the surface to measure the in-plane displacement. So in this case, we put the grating on the specimen. This specimen is a long rubber plate with 3 holes. So the grating is recorded by this digital camera. This point shows the center of the pixel point. Then we can obtain this digital image. So if we extract every almost 1 pitch size, so in this case, we extract every 4th pixel, then we can obtain this image. This process called downsampling. But if we extract, this is the first pixel image of the 1 pitch. But this one is the second image, third image, and 4th image. Then we extract every 4 images. We can obtain this moiré fringe pattern. In order to clear the image, this extracted image is obtained by linear interpolation. Then we can obtain this smooth fringe pattern, moiré fringe pattern. So we can obtain the same pixel points, phase shifted grating pattern, moiré fringe pattern. from this phase shift brightness, we can analyze the phase distribution. I'm sorry. Then we can obtain the phase distribution. The phase change, 2 pi phase change, gives a one pitch displacement. So this one gives a displacement distribution. By differentiating the displacement, we can obtain the strain distribution from this. It's easy to obtain the displacement in each phase strain distribution. So in sampling model method, phase is analyzed from a single shot image, such as almost the same as the OPPA method. This one is analyze the movement. The grating is pasted on the rubber specimen, and here is a fixed. Here is a free. Here is a space. Then the fringe pattern is different. In this case, only the upper edge is deformed. So we can easily obtain the displacement distribution by using this OPPA method or sampling moiré method. We apply this method to measure the vibration of tuning fork. This is the tuning fork, U shape like this. We paste the grating on the surface. By hitting this end, it vibrates. So the vibrating grating is recorded by this camera. And we also use the laser displacement meter to check the vibration and to check the our measurement method. This is the result. This is the image of the grating. This is the displacement difference. And this one is power distribution, scale of amplitude. And this is the phase distribution. So the movement of left side and right side movement is the phase is opposite. This one is a phase movement. By moving changing the phase, it moves like this. The phase is different, right side and left side, because vibration is opposite movement. This is the first mode of up to 137 Hz. This one is the second mode image, power image, and this is the movement of the phase by moving this one. So here is a node. I'm sorry, this one is not good here. So now, today, last night and tonight, we are measuring the floor slab and girder of highway bridge. Here is the back side of the road. We projected the grating by projector, and the grating image is recorded by our camera. So tonight, just now, we are measuring the deformation of this bridge. So it's easy to measure the vibration of the object by using our method. So in this bridge, there is so other company uses optical fiber grating. And here is the accelerometer, but it doesn't give the distribution so fine. In conclusion, we propose a new shape measurement method, OPPA method, to analyze out-of-plane vibration mode. And sampling model method is applied to analyze in-plane vibration mode. It is possible to measure whole surface vibration with high-speed recording and high-speed analyzing. It is especially useful to analyze transient vibration. It was applied to car and tuning fork vibration. Now, just now, we are measuring the displacement of highway. We don't have so much time. Now, this is a building in Chicago. If we measure the vibration of building, we must put the grating on the building. But grating, the building has a grating. This is a window or tile which has a grating in. So by analyzing the phase distribution of this grating, then we can obtain the phase distribution. By analyzing the phase distribution, we can easily obtain the moving building during the earthquake, or after earthquake, we can easily detect the building. It's easy to calculate the phase by using our method. That's all. Thank you for your attention.